Hey, I'll be right with you. I just have to finish this one clash match. I'll be really... Last time was supposed to be the last time, but never stop on a losing streak. Or a winning streak. Either way, it should be over with really soon. I got him on the road. God, giant! Get him. No. I'm gonna... Oh, shit. So, Electron configurations. Sorry. Great game. Don't get me wrong. Worth every blood vessel I've popped in the last month. But Electron configurations. Maybe you are equally frustrated with Electron configurations. But so trying to remember that, whole filling order 1s2, 2s2, and so on. People struggle with. And there's a few ways you can learn it. I guess you could just try it by rote memorization, but that trick never works for anything in this class. So please don't do that. But some people, they find out about this, one table where you put the row, where you put the subshells and the shells in certain rows and columns, and you got diagonal arrows going through the thing in a certain way. I really don't like that memory aid, because you got to remember how you set up the columns and how you put the row. You got to remember which way the arrows go. You need a memory aid for the memory aid, which to me doesn't make for a good memory aid. For me, the best way to understand how Electron configurations work, the best guide to help you figure out almost any Electron configuration, is a table, but it's a table that you don't have to memorize, and you probably will be given one come test day, and that's the periodic table. See, you probably remember Mendeleev, that old Russian guy who was the father of the periodic table. And when he was putting his table together, he was doing it by chemical properties. Lithium, sodium, potassium, they all have similar properties. So, he put them all in the same row. We flipped it, and now they're all in the same column. But as we learned more about how atoms work and how they're structured, we realized that the reason that all the alkali metals behave in similar fashions, and the reason all the alkaline earth metals have similar chemical properties, is because they have similar electron configurations. So our modern periodic table is by and large built on the electron configurations of the elements. And so for Gen Chem students, that's good, because you can use that to help you keep all that 1s, 2s, whatever stuff straight. So the first thing we're going to do is we're going to split our table up into 4 blocks. The first 2 groups, the alkaline earth groups, we're going to call those the S block. The transition metals, we're going to call the D block. I know it's starting to sound a lot like prison, but hang with me. The main group elements, or the rest of the main group elements, we call the P block. And the intertransition elements, lanthanide, actinide series, whatever you want to call it, we call that the F block. So next, we're just going to go down row to row, or period to period if you want to be picky. And as you go down row to row, there's a couple things to keep in mind. Though, let me start by saying this little trick only really works starting with period 2, mainly because helium got moved more or less from being above the alkaline earth metals right next to hydrogen. It got put over above the rest of the elements in group 8A. Even though it has similar electron configurations with beryllium and everybody else in that group, chemically it behaves more like the rest of the inert gases. So that's not that big of a deal, though, because you learn pretty quickly just from practicing a couple of configurations that every electron configuration starts with 1s2, I guess except hydrogen, which is just 1s1. But starting with period 2, you're going to just, as you go through each block, remember that with the S and P block, whatever period you're in, that's the N in that part of the filling order. So as you go through period 2, you're going through the S block and the P block. So that'll be 2S and 2P. Period 3 is the same way. You're going through the S block, 3S, P block, 3P. Going through period 4, 4S. Now when you go through the D block, you have to remember the N is equal to period minus 1. So we're in period 4, 3D. Now we're back to N equal period with 4P. Period 5, same way. 4S, drop it down 1, 4D, back up 5P. Going through period 6, again, you start with the S block, 6S. And remember, this is where the F block belongs in the main part of the table. The only reason we pulled it out is to basically have the periodic table fit on an 8x11 sheet of paper, and so it's not twice as big or take up twice as much space on the wall when you have the big charts. But when you go through the F block, remember that it's period minus 2. So the lanthanide row, that's part of period 6. So 4F. Now you're going through the D block, 5D, and then back through the P block of period 6, 6P. Period 7, same thing. 7S, go through the F block, minus 2, 5F, back through the D block, minus 1, 5D, 6D, and then going through the P block, N equal period, 7P. So that bit of information, that's the same stuff you get from that diagonal arrow table thing that I just said I don't like. And another reason I don't like it, besides the fact you need a memory aid for the memory aid, is that's all that thing gives you. But with the periodic table, once you understand how the table is connected to electron arrangement, you get a lot other information from the periodic table. For example, if you look to see how we divvied up the blocks, the S block is made up of 2 groups. And that reminds you that the S subshell can hold 2 electrons. The rest of the main groups, the P block, has 6 groups in it. And that reminds you that the P's can hold 6. There are 10 groups in the D block, which reminds you that the D's can hold 10. And there are 14 groups in the F block, same number that the F subshell can hold. So another thing you get, and this is probably my favorite thing about using the periodic table as a guide to electron configurations, is where that element is on the periodic table gives you an idea of what its electron configuration probably ends with. So let me show you what I mean. So for example, let's look at oxygen. If you work out its electron configuration, it's 1s2, 2s2, 2p4. But notice that oxygen, where it's located in the table, it's in the second period, it's in the P block, and if you count which group in the P block it is, it's 1, 2, 3, 4th group in the P block. So look at another one. We'll look at iron. So its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So if you look at what its configuration ends with, it's in the D block and it ends in 3D, and it's in period 4. So remember, in the D block, the N is period minus 1, and it's in the 6th group of the D block, and it ends in D6. So when I do electron configurations, and by the way, I know with iron it looked like I zipped through it. I don't have all 118 whatever memorized. It's just I knew where it ended, so I just kind of zipped through and did it really quick. And so what I like to do normally when I'm kind of showing students how to do this is I like to start at the end and then start with 1s2, because every electron configuration. The first two go in 1s. And then just use the periodic table and kind of work your way down until you get to the element you're looking at. So just to kind of prove that I'm not just picking ones that work, I'm going to everybody's favorite random website, random.org, and I'm just going to have it give me a random number between 1 and 56. And I'm going to do it sort of live because it's pre-recorded. But you know what I mean. And there's a reason why I'm cutting it off at 56. I'll tell you more about that toward the end. So give me something. 27. So 27. That is cobalt. So cobalt, it's in period 4, and it's in the D block, which means that it ends, it should end with 3D, because again, D block, it's period -1. And if you count, it's in the 7th group. And actually, notice that the second number for the first row of the D block elements is the same as whatever group it's in, like 21, 22. So that's a handy trick to learn. But it's in the 7th group of the D block, which means it should end with 3D7. So again, the first two always go in 1s. So we're going to start with 1s2, like we always do, except hydrogen. And from there, we just kind of go down the table. So we go through period 2, we're going through the S block and the P block. So it's 2s, 2p. 2 groups in the S block reminds us that it's S2, and 6 in the P block reminds us that it's P6. Period 3, same thing. You're going through period, or the S block and the P block. So 3s2, 3p6. And now you go through the period 4. You go through, start by going through the S block, so 4s2. Now we're in the D block, and we've already said that's what it should end with. And one way to check your work is, remember the superscripts, that's the number of electrons. And we're talking about cobalt, which as a neutral element has 27 electrons in it. These things should add up to 27. And I think they do, yeah. So let's try another one. And again, random, give me another one. 21, that was real close. Give me one more. I'm only doing 20s. 29, one more. I'll be 20s. 44, okay. I just don't want them all to be in the 20s, that's all. So 44, that's ruthenium. So again, we start with, I like to start at the end. So it's in period 5. And it's in the D block. So it should end in, whoops, not 5D, 4D, because again, period -1. And since it's in the 6th group of the D block, it should end in 4D6. So again, first two always go in 1s. To get everything between 1s and 4D, we just start at period 2 and work our way down. So again, we're going through periods 2 and 3, through the S block and the P block. So 2s2, 2p6, 3s2, 3p6. Now you're going through period 4. So you start by going through the S block, as you normally do, because it's at the front. So 4s2. Now you're going through the D block. Remember to subtract 1, so 3D. And again, you don't have to remember there are 10 electrons in a D subshell. Just count that there are 10 groups. So D10. Next, we're going through the P block of period 4, so 4p, 4p6. Now we go through period 5, so we're almost there. 5s, 2, and we've already said it's going to end in 4d6. And if you double check your superscripts, they should add up to 44. All right. So one more. Let's see if I can get a P block or an S block element in there, so they're not all transition metals. Give me one more. 26. You really like the 20s today. Random. Or is 26 one? No, that's iron. I already did iron. Thinking about it. 24. Again, the 20s. It's random.org. 44. I just did 44. 1. Hydrogen. Really? It's like the old Google Hangout shows I used to do. 41. Medium. No, at this point, it's just on principle I want to do. Okay, 33. All right, there, finally. We'll do one in the P block. Although I got to make another. There we go. All right, so 33 is arsenic. All right, so arsenic is in the P block, and it's in period 4. So it should end in 4P. And if you count, it's in the 3rd group of the P block. So it should end in 4P3. So again, first 2, always go in 1s2. To get everything else, start going down row to row. Go through the period 2. You're going through the S block and the P block. Period 3, same thing. S2, P6. Now you're going through period 4. So we're almost there. 4s2. Now you go through the D block. So remember to subtract 1, 3D, 10, because there are 10 groups. And we said that it's going to end in 4P3 already. All right, so from there you kind of get how it works. Now, the reason that I had it end at 56 is because I didn't want to randomly get one from the F block. Because I said earlier that, you know, using the periodic table as a guide, you can almost get the right configuration for every element. But that doesn't work for every element. For example, copper. If you go through the motions like we just did earlier, its electron configuration should end in 4s2 3d9. Because if you go back and look, it's in the 9th group of the D block, period 4. But experimentally, its configuration is actually 4s1 3d10, because for whatever reason, copper would rather have a filled D subshell than a filled S subshell. And these are what we call anomalous electron configurations, because there's some other stuff going on, like, you know, filled D over filled S, that we really don't get into in Gen Chem. And again, the reason I skipped the F block is because there's a lot of anomalous configurations in that block. But, you know, if you want to practice any of this stuff, again, you can pretty much pick any element from, I used one from 56, go nuts and use 1 to 118 if you want. And you can find the electron configurations just doing a quick little Google search. Or if you go to Wikipedia, I think every element now, they give you the electron configuration. Just keep in mind that the electron configuration they're giving you is the actual configuration. So the predicted configuration based on the table may not always be what it really is. Did I say that right? I don't know. Forgot what I said like the last 5 seconds as I was thinking about the next 5 seconds. That happens sometimes. But anyway, if you look it up, what you might see may not match what you got, even though you thought you did it the same way I did those last 3. But odds are, if you're pretty sure you did it right, it's probably an anomalous electron configuration. And one sort of telltale sign that it's anomalous is like with copper. You normally follow the off-bow principle and fill everybody up in order. You know, 1s, 2s, and so on. But if you see some weird stuff where one didn't get filled before the next one had electrons put in it, again, like copper, that's probably a sign that you got an anomalous configuration, and you were probably correct. So yeah, just keep working at it, and pretty soon you'll just be zipping through those electron configurations, no problem. All right, so that's it for now. I didn't talk about rare gas configurations or some other stuff. I'll save that for another video. But for now, I will see you guys later. Son of, I'm gonna break this losing streak if it kills me, you son of a